Hi everyone. Today I will present the simulation-based methodology that we are developing at Ghent University as part of the Heritage project, which is an Horizon project on the renovation of heritage buildings. And as the basis of the methodology actually starts with research in the 90s. So it's the model, the so-called VTT model, or the Vitanen model, it's also called. And he researched surface mold growth on wood-based materials. So that's kind of a known model, let's say, but then actually there has been further development of this model by VTT together with Tampere University. And so now it's actually called the Finnish mold growth model. The main addition later on was actually that they managed to more generalize the methodology. So they found categories to put materials in based on their sensitivity for mold growth. Which allowed to have a more broader use of the underlying model. The output of this model is what they call is a so-called mold index, which is a number between 0 and 6, where 0 is, well, there's no mold growth, no activity, or no detectable activity at least. And then first there is microscopic activity, and then moving on to the more visual activity and ending in index 6, which is like, very heavy, tightly grown molds on surfaces. So generally speaking, we kind of want our buildings to be below 1, let's say. If we go back to the previous graph, you actually see that there is this clear threshold value at 80% relative humidity. So below that, based on this model, you could say, well, we don't expect mold growth issues. So in other words, if you put it in a formula, this means that the indoor vapor pressure should be below 80% relative humidity of, and this is important, the relative humidity calculated at a possible cold point in the space, so a thermal bridge typically. If you look at the formulas, you actually have 3 ways to avoid mold. So you can increase ventilation, which means that you lower the moisture load of that building. You can increase indoor temperature, because if you increase the general indoor temperature, also the temperature on that surface will be higher. And then thirdly, you could, of course, have impact on the thermal bridge itself. So more insulation, making sure there are no thermal bridges. So try to avoid it by design. This last approach in Belgium is kind of the standard, because how it's done today, or what the common practice is, and how architects, for instance, design the buildings, is to have thermal bridges with a temperature factor, which formula on the slide, of above 0.7. So based on research on what are typical indoor conditions in Belgium, typical ventilation rates, and then define, well, let's take a relatively high internal climate class, number 3. Based all of that combined, well, we decided, well, if our thermal bridges are above 0.7, we expect things to be fine. The thing is, because of this very prescriptive way of dealing with things, you can get in a situation as a designer or as an architect where this is actually very stringent threshold value. Because if you look at heritage buildings, and that's of course the topic of the research project, where you have these very lovely facades, but also antique interiors with high heritage value, well, it's not always easy to fix the thermal bridge. It's not always easy to get a number as high as you need to have for according to Belgian practices. So that's why in the project we opted to take a step back and not only try to solve it by design, but really look into combining our building simulation models, which is a combination of thermal and airflow models. We couple it to a thermal bridge estimate, so to have an accurate surface temperature. Then we couple an EMPD model to it. It's a moisture buffering model, which makes sure that the relative humidities in the space are representative and realistic. And then we used that, so we implemented the finished mold growth model within the environment. So, well, we coupled everything to have a mold growth index as an output of our simulation models. To show you a workflow or how that's done, we've did some initial experiments. And I'm going to show one of them, and it's the Heritage Bay window. So the typical archetype we have, it's very thick brick walls, but then there's like one light wooden structure extending outside of the building with typically very thin walls and thermal bridges as a consequence. So what we did is, okay, we looked at those bay windows. We derived technical detail of it, and then you can, with existing software like Trisco, do a simulation to get the temperature factor of that thermal bridge. So in this case, it's indicated with the arrow. There's a small, the lowest temperature can be found just beneath the, well, in the wall, but just beneath the ceiling. And this then is serves as input to our simulation methodology. Of course, we need other inputs. So let's start with the most typical situation for that room in the house, which is a bedroom. So I'm assuming here a two-person bedroom. So they're asleep, but then there are two more active moments with more moisture production related to that. And then she defined the temperature profile. Notice here that it's not always 20 degrees in these spaces. So based on measurements, we derived this profile. So people tend to keep their spaces at much lower temperatures actually, well, during the year to save energy. Combine this with relatively low air change rates just because of the leaky windows, so there's no mechanical ventilation in the basic situation. You get a very bad result in the sense that there will be mold growth, or according to the model at least. Of course, this assumes that people never open their windows, so probably this is a bit of a negative situation. But yeah, you can't really count on people knowing when to open their window, and also if they don't do it at the right time of the year, it's also a bit tricky. So assuming for design that they don't open it perfectly, I think is a good assumption. But anyway, so this is a start situation. So with our model, we can then continue and try to make some variations on the design, on the heating system. So here are some results. So first, we just tried, well, what if we ask people to heat up their spaces? Of course, not the most energy efficient strategy, but still, it actually didn't make that much of a difference. In this case, because the thermal bridge is very bad, we also said, well, if you're renovating, probably you're going to add ventilation for other purposes than only mold growth. But well, what's the effect? And there you also already see quite a big improvement. But actually, if you don't want to alter the thermal bridge characteristics, so not at all, you need the two to be combined, in this case, to be below 1. So it's technically possible to avoid it by just changing the temperatures and airflow rates. But of course, this is not a really energy efficient way of handling it. So let's look into something in between, because actually there are smart and not as invasive ways to fix these thermal bridges. So what you see here is the same detail, but then with some insulation in the right spaces, but it's really with very low impact. And actually you can already get to a temperature factor which is 0.2 higher. So it's much better. But looking at the results, not enough. So in black, you still see the same bedroom as before. And then the second line, one line down, is with the increased temperature factor. Here, just adding ventilation, and this is not more than necessary according to our nominal standard, actually already gives sufficient, well, make sure that the mold growth isn't happening as much and everything stays below 1. So that's actually already a good sign. So a bit insulation, not intervening too much on the heritage value. Adding ventilation in this case fixed it. But then we need to stay robust because a building can be used differently throughout the year. So maybe at some point it becomes a living room. So that's another test that we did. So assuming a 4 people family. So maybe there are offices on the ground floor and only the top floors are inhabited as they're in a residential setting. So assuming 4 people with some time in the morning and a longer time in the evening, different temperature profile and the same characteristics as before. Well, higher moisture load, so higher problems. But actually, turns out, based on our models, we just tried increasing ventilation, so adding the normal one, adding even more ventilation. So it's about the air change of 2.6 is basically calculated as being 40 cubic meters hours per person. So it's a higher standard, but not necessarily that high. But only ventilation there again didn't solve the problem. But if you increase again if you increase the temperature factor to 0.5, again, it's not some crazy intervention. It's quite doable. If you combine that with normal ventilation standards, then you actually manage to push down the mold indexes quite a lot. So just an example. So in this case, it's also kind of basic assumptions for temperature and humidity, but the whole thing is set up to actually be coupled to our simulation environment and actually couple it to the transient simulations that we will do in the project, actually investigating different ventilation strategies and controls. But this will be our way to check if none of what we're doing actually increases mold risk or mold growth risk. And we want to, of course, make sure that designs are taking care of the designs that we propose don't increase mold growth risk here. Finally, I just need to thank the partners in the project, and I'm happy to hear your question on this.